Welcome to After Hours Engineering, episode 15. In a previous episode, we introduced ourselves to the ZICSR extension, otherwise known as the CSR instructions. In this episode, we implement and make use of those CSR instructions. Now, there are many ways to implement CSRs because there are a lot of them, but as such, we are implementing only a bare minimum of them in order to support a very simple parallel I/O protocol. To add CSRs to range of RISC, we're going to need to modify and enhance some sections of the code. For example, the control matrix, the range of RISC core, the CPP loop, where we'll inject an interrupt, a single line assembler, the enums and defines, and then a GTK wave filter, and finally machine code. So we'll swallow the red pill and enter the matrix. We start with the CSSR instructions first, but there's a big question. Where are the CSRs? Well, initially when I started designing this, I thought of putting the CSRs in their own module. Fortunately, that turned out to be a whole lot of muxes and wires and everything that needed to be added so that the matrix could talk to the registers and vice versa. And it seemed like to me, in my design at least, that the CSRs really belong inside of the control matrix. And so ultimately, that's what I decided to do. And so here we have the design for the CSRs. They're now inside of the control matrix. So the question we have to ask ourselves is, we know that the CSRs are going to move data, but why and where? Well, for one thing, the CSR's job is to make a copy of the CSR and move it into the register file. So we need a data path coming out of the control matrix, because that's where the CSR is, and route it down. And we'll use this fourth input that we haven't been using so far. So I'm glad we had a 4-input mux down here. And we'll route that into the register file during one of the cycles. We also need to read the mask, the bit mask, out of the RSA register, which is technically RS1, and route that in. So we need another path up here in order to support that. So these two paths here and here will support all the CSR instructions themselves. We'll talk about this extra path once we get to the machine return address. For the machine return instruction, we need the ability to load the program counter with a return address of the instruction that's just past the point of where the interrupt occurred, and we need to be able to store the program counter in one of the CSRs once interrupt has occurred. So we have two paths for that. We have a brand new routing of the PC over to the control matrix, which we didn't have before, and now we have a output of one of the CSRs routing into the PC mux, which will give us the ability to load in the program counter with the return address. So we need these two new paths on top of the two that we just added prior. And of course, we need the interrupt signal itself. So when the interrupt comes in, it will trigger a process at the end of an instruction, when an instruction is being retired. Now that we know the four paths, this one, this one, this one, and this one, and the one signal that we have, we're ready to take a look at some HDL code starting with the control matrix. So let's go over to the control matrix and take a look at what we've done. Here is the control matrix. We've seen it before. However, there is some new differences and changes to it. Starting at the top, as usual, we've got our two new inputs here, the RSA feeding from the RSA register, and we're routing our PC into the control matrix now. This is for storing it in the MEPC register. We come down here, we've got two more inputs or outputs. In this case, we have the RSA load flag so that we can load it once and control it while we're in specific states dealing with the interrupt. And then we have the RD, or the destination register. This is actually going to double for either loading the program counter or loading the register file in this case. We scroll on down here, we'll see some new signals for the CSR. These are all the internal wires and logic that support the CSR instructions itself. So we come up here. We have a detection as to whether it's an actual CSR itself. Is the destination register X0 is RS1 X0 in and of itself. Here is our 5 CSR registers that we'll manipulate. This is the address that determines which address that we're speaking of. We translate the address from its hex address, generally starting at 300, and translate that into one of these specific registers here. We'll see that in a second. The algorithm for applying the or the not ands, the destination for routing to the outside. The 3 variations on the CSR instructions are their immediates, and they're always pulled from the same place in the instruction. Whether we've even detected an interrupt coming in from an external device, in this case is just a single pin, whether we're going to sustain the interrupt signal between states, and indicating whether we're going to write to the CSR. Again, remember back in some of the previous episode we talked about different combinations of X0 and 0 values may actually prevent us from writing into the CSR, so we need to control that. And the immediate field is held up here in the top 12 bits. We've also added a couple of initialization sequences for the M status register. We might want to start off with global bits enabled and maybe have some sort of enablement bits set up in IE. In this case, we're looking at different types of values, so we can test whether we're clearing and setting instructions. And if we come down here, we'll now see a whole new section. It's relatively large, that contains everything necessary to set up default values for this. Again, this is the section that deals with reducing inference on latches, and in System Verilog it will not let you move forward unless you explicitly turn those off. So here we are, we're setting up our default values for all those flags we just discussed, and we're also pulling out of the instruction the address of the CSR, which again is up in the top 12 bits. We're also checking to see that if it is an opcode of I type E and the function is not equal to 0, because if it is 0, we know that it's an E break or an E call instruction, then we know we have a CSR instruction. If it is, then we go ahead and start extracting some information out as to whether the destination register is X0 or RS1 is X0. We know that there is only one scenario where we don't read a CSR register, and again, going back to those diagrams, we'll know what that is because the destination register will be X0 and the instruction will be CSR RW. If it isn't, then we can read from the registers, and again, any attempt to read from the registers can potentially cause a side effect because any of these registers, as mentioned, can be physical hardware. We take that address, for example 0x300, and we match it up with one of the hex values that we've defined inside of our types enum file here. So if we come over here, we can scroll down and look for the address of any of those registers, because this is the number that goes in the instruction. We don't put 0, 1, 2, 3, 4 in the instruction. We actually put its address in the instruction. Again, we come down here. If the destination is X0, we're going to be going straight to the CSR, writing only. We're not even going to set the CSR write flag. If it is the immediates or the resets or the clears, or in this case, the immediates, then we know we're going to apply an algorithm. For example, if it's the clear, we do that not and with the data itself. So we're knotting the mask and then anding it with the value that was in the CSR register. And the same thing with the set. We're just simply ORing the mask with the data itself. And then finally we get down to the bigger chunks of code. The decode statement needs to have a little bit of an enhancement on the I type E instruction. Before, if you remember, we only detected the E call in the E break, but now I've had to modify it so that it's a bit more specific on the top 12 bits as to what's going on. And we know that for the return, the machine return instruction, this is the combination of bits that signify that it's an MRET instruction. That's what changed there in the decode statement. So now we're ready to come down to the execute statement, and this is really huge. We'll have to break this up into several sections and go through them. These are the I type CSR instructions. The very first one that we have is the CSRW instruction. And again, referring back to the diagram, we know that if the destination register is X0, then the only thing we're going to do is write to it. We're not going to do anything else, and then immediately transition to the prefetch instruction. Otherwise, we want to transfer the CSR value to the destination registers, which means the control matrix starts to send out signals to the other components in the diagram, the data flow diagram. And in this case, we need to tell that WD register to select the data coming from the control matrix that has a CSR value in it. And of course, we need to set the write flag low so that we actually write to the destination register. And then we transition to the execute sequence. That's what this is going to go to. However, if it's a set or a clear, and this time we're looking at the RS1 value to see if it was X0, then we're going to do almost nothing at all. We're going to just simply go straight to the prefetch, and that's it. And of course, we look at the immediate variants, and they all will do the same thing. They're going to set up the WD to route the CSR value into one of the register files specified. And then we transition to the load, which is down here. The load will set the RSA load flag to disabled. It'll actually maintain its disabled state. We'll now finally turn on the write flag for the CSRs, and depending on which one of the instructions again that it was, we're either going to set the CSR data to the incoming mask or data. In this case, it's not a mask, it's straight up data that we're going to route right into the CSR data. Now this value right here, we'll see way down below in the synchronization block, we'll write the data into one of the selected addresses. Otherwise, if it was one of the resets or sets, we're going to take that algorithm we did, whether it was the or the not and move that into the register. Now we're at the machine return instruction, or the MRET. And in this particular instruction, for this state, we're going to do two things at the same time. One of them is to move the MEPC into the program counter. Now because we've chosen to use I-align of 1, which equals 32 bits, the lower 2 bits will always be 0, and so we're going to force them to 0, no matter what. So we'll move that value into our RD logic statement so that it's routed out of the control matrix and into the MUX. And of course we need to select the field coming in on the MUX, the channel, so that's what this is. And then we need to enable the load on the register itself. Also, the second half of this is to start restoring some of the states of the machine itself. We know that when the interrupt occurred, we took MIE and moved it into MPIE. So we're going to reverse that process. First, we grab the status register so we can modify it. And the reason why we do this, by the way, is because the M status register is being manipulated inside of a synchronous block. So you can't manipulate this register directly inside a combinatorial loop or a behavioral block like this. You need to move it into another register so that you can manipulate it. And that's exactly what we're doing here. We're going to take that MP and move it into the MI slot within the same register itself. And then we'll clear out whatever value it was. And finally, we'll set the address for the writing sequence to the appropriate address that we want. And then we move on to the clear statement. So these two things will happen at the transition to this next state down here. And in this one, we're now done with the interrupt itself. We'll turn around and remove or clear out that pending bit, because this is the pending register. And then we'll set again the write for writing, and we'll set the address so it selects the correct CSR register to write this CSR data to. And finally we transition to the prefetch state. This one's been modified for the CSRs such that at the end of every instruction we transition to the prefetch. Prior we were kind of mixing it up. Some would go straight to the fetch and some would go to prefetch. Now all the instructions go to prefetch, and we do that because at the prefetch stage the instruction has retired, and that's where we've chosen to do any kind of checks that we want on any kind of CSR registers. In this case, we're checking to see if an interrupt occurred, and we know that when the pending bit goes high. but we can't honor it unless any of the interrupts have been enabled, and they're hierarchical in nature. This particular register holds the enablement bit for just M mode, and this particular register holds the enablement for all of the interrupts in general. So the global bit must be a 1, the M mode must be a 1, and of course we must have a pending bit set, which means we've detected an interrupt. If we have detected one, we're going to sustain a signal for holding the interrupt value itself, and we're going to set our write flag to the CSR's high. Again, we copy the specific register, in this case the M status register, into our holding register here. We're going to back up the MIE into the MPI, which is what we saw up above, but now we're doing it in the forward direction. We're going to clear out, or in this case we're going to disable all global interrupts so that we're not bothered while we're in the trap handler itself. And then finally we're going to set up the address for the write, which we'll talk about once we get down to the behavioral blocks down below, the synchronous blocks. If it didn't detect an interrupt, then we still want to check to see if we need to sustain the signal and maintain a write state, and then transition to these extra interrupt states, and we're going to hit those in a second right down here. But if it wasn't, then we just simply go straight to the fetch, nothing else. We set our memory read as we usually do to fetch that new instruction, and we go to the fetch state. IRQ0 is for finishing off the interrupt itself. In this case, we're going to set up, we need to first move the program counter into the MEPC. This is the address of the instruction after where the interrupt was detected. And then we set the MPC address, we set our write flag again, and we clear the sustain because we no longer need to sustain that. And we now move to instruction IRQ1. In this particular state, now that we have detected an interrupt, we need to jump somewhere. And in this case, we need to jump to a handler. The address of that handler is held inside the MTVVec register. Where was it loaded? It was loaded during the boot process, which we haven't talked about yet, but we'll get there soon enough. But it does hold the address of the trap handler itself, and we load that into our RD logic variable. So again, we can route it out to the program counter, which means we need to select that PC source and enable it. And when we move to IRQ2, the program counter will have finally been loaded. And you guessed it, the last thing we need to do is go straight into the fetch. Why? Because that program counter now has the address of the trap handler, and it will load that instruction in and begin executing the handler in and of itself. We finally hit the bottom of the control matrix, and we've added one extra behavioral block down here, a synchronous one. This one is still unchanged, so we'll collapse that. In this particular one, we're doing two things. One is we're looking at that write flag that we've been setting up above to see where we need to write this particular data to. That's all this does. If the address was the M status, then whatever was in this data here gets written into that status register. That's it. Remember that the MTVec has a value in it that we load during the boot sequence. This is going to be set right here below. This has our address of where the interrupt occurred, and these have enablement bits in them. So if we look down here to this section, this is the one that's monitoring the incoming signal from an external device. In this case, when the interrupt goes low, from high to low, we immediately turn around and set the pending bit inside of the MIP register. So that the next time that we hit the prefetch sequence, that again, that's at the end of an instruction, we'll check to see whether this bit is set, including the enablement bits, and we'll execute the trap handler yet again. And we would keep doing that as long as the interrupt is being set. Now it's more complicated than that, but we'll talk about in later episodes on how we can synchronize both an external device and the softcore CPU at the same time so that they're not running into each other. And last but not least is the bottom half of the control matrix, where we finally route the two pieces of information to the outside world. So that's it. That's the entire control matrix from bottom all the way up to the top. With the control matrix set up and ready to go, we now move on to the RISC processor itself, the core, and add in the few items that we need to add based on the data flow diagram. Starters, here's the top of our module, and we work our way down through all of the pre-existing wires, but we're going to add a couple more to support the CSRs. One of them is loading the RSA register, and the other one is the data coming out of the control matrix that can either go into the program counter or into the registry file. That's what this one here is for. And of course, we have our new fields right here. We have that interrupt enable coming into our matrix. We have the program counter coming in and the RSA output coming in. At the bottom, we have our two new outputs, the RSA load flag and the RSA data. That's excellent. We need to modify a few items in here, and one of them is the PC MUX right here. This was a MUX 4, now it's been expanded to a MUX 8, and we have our new piece of data being routed into it right here. Excellent. Then we come down to the WD MUX, and we're finally using that one extra input channel right here, and that's that data that's being routed into the register file here. So that's excellent. There wasn't much that we needed to change inside of this, just a few touch points, and that's it. Now we move on to the test bench, and the one and only place that we'll make a modification is the place where we will inject an interrupt in. So we'll move over here into our loop statement within the test bench, and we'll add a couple of lines of code. We've picked two particular picosecond times where we know an instruction is in progress, and that's where we will toggle the interrupt flag to low and then bring it back high 3 picoseconds later. That's it. There's nothing else. The bench stays exactly as it is. All we're doing is injecting an interrupt signal. Now we're ready to make modifications to the single line assembler to add in the assemblers for the MRET and the CSSR instructions. We'll start with the CSR first. So I've added a new file, I_CSR, and all it does is it reads in the instructions of different formats, parses them up just like before. Here we're detecting a word and we're translating it into an actual address. This will be stuffed into the bit stream of the instruction itself. Then we come down here and start breaking down the various fields that we found out of it and it's sticking them right into the instruction itself. And again, because of the logical order versus memory order, we reverse everything as we're reading them. And so we know that 0 through 11 for this particular field will have the CSR address in it. Then we come down here, we fill in the instructions for the RS1. We then decipher what type of CSR instruction it is and embed the appropriate function 3 in it. And finally we set up the hard-coded instruction itself. And then of course the destination address. And then we come over here for the MRET, and it's the simplest of all of our assemblers. It doesn't even try to parse the file. It just simply detects that it's an MRET instruction and then hard codes in everything into the instruction itself. About as simple as it gets. Now we look at the enumerations and definitions. First up we have the CSR type, which is based off of function 3. So we have 3 bits for each one of these. And then finally we have the register specifications themselves, and this is basically a word versus an address. And for us, all of these registers start at address 300 out of 4096 possible ones. On the definition side, we've set up a couple of definitions for the address size. We know it's 12 bits. There's 9 registers, of which we're only using 5, and here are 8 of them. Right here, we know we're using different bits out of different registers. We know these are 2 mirrors of each other, so their numbers will always be the same. We're not using cause right now, but we are using the M status registers, and these are the enablement bits. This with the previous value and the current value of the enablement bits. Of course, when we modify our enumerations, we always have to make sure we come over here and update the filters for the GTK wave files. So I've gone ahead and added in the different types of new signals that we have and adjusted the numbering so that they come out correct inside of GTK Wave. Forgetting to do this will cause GTK Wave to look very unusual and generally wrong. Now we're ready to start writing machine code with our newly minted instructions. We'll begin with the CSRRW instruction right here. So we know using our assembler we can grab this assembly right here, run it through our assembler, and out pops this number. And of course we have our ubiquitous e-brake so that we don't run on forever, and the program starts at 4. So let's load this into RAM, which I've already done, and I've already configured the memory to point at that RAM file. Here's the output of the simulation, and as usual we go through the reset sequence until we hit our first instruction, which is sitting at the address 4. That's where the reset vector put us to. We can see there's our instruction we encoded. If we come down here, it's beginning to execute the instruction itself, and what that's going to do is load in the destination register, which is X2, with the value. So if we come down here, we want to know, how did the value get up there? Well, we know that the status register, which is what we're trying to back up into a destination register, eventually gets loaded into the CSR data. That is then transferred to the WD source output, and eventually write signal goes low. We write it into the destination register. Excellent. That's exactly what we were expecting. So the next state is the load portion of it, and in this case we're going to take the RSA value. It will be written to the CSR data value, which then turns around and it eventually is written into the status register. And that's exactly what we wanted. The RSA was coming from one of the source registers, which in this case was X9. So there you go. This instruction is executing exactly as we expect, and of course it eventually runs into the next instruction, which is the e-brake. Now we'll take a look at the instance where the destination register is X0. So I've created the assembly for it, assembled it. Here in the simulation we can see we've hit the instruction and it's immediately gone to the execute stage as expected. It went through the decode, then to the execute. But notice that there isn't the other second state of this instruction. It goes straight to prefetch. We'll know this is because the register, the destination register, is X0, and down here that's all we're doing. Here we're grabbing the destination register's value, which is X9. It gets moved over to the CSR data and eventually written into the actual CSR register, which is the status register in this case. And that's what we expect. Excellent. Now we take a look at the instance where the RS1, or the source register, is actually X0. In order to test that, we'll need to switch over to the set or the clear. In this case I'm using the set version of the instruction. And here I have the assembly, and I've already run it through the assembler, put it in there, set up the memory, and we're now ready to simulate and see what happens. We should see that we only read a CSR and nothing else happens. Here we are in the simulation, and as usual we're right at our instruction. You can see again it's a very short. We didn't hit the second state of the instruction, just the first one. And if we scroll down to the bottom here, you can see that all it has done is read the status register, which shows up in our CSR data. But nothing else is around here. We don't have any reading going on. All we did was read the value, which was 08, and loaded it into the CSR data logic value in the control matrix, and that's it. So this is doing exactly what we expect it to be doing, and of course it goes off to hit the break instruction. We'll test one more of the set instructions because all the rest of them pretty much do the same thing. They'll either set or clear bits or completely write a value into one of the CSRs. In this case we're testing where neither the destination or the set source is X0. So here's the assembly instruction. We've coded it up right here. We preload X9 here with 5. So if we come up here, we know that the status register has an 8 in it, which is right here, and our mask, which is 5, is this right here. So when the instruction executes, it'll set each one of the bits up here with anything that's a 1 down here, which means we get a 1 from the original 1, a 1 that's been set, a 0, nothing changed, and another one was set. That answer is D. So we should see that the status register has D in it when this code runs. So I've already set up the simulation. Let's check out the results. Here we are in the simulation, and we've just run the load instruction, and at the end of it, during the complete, it moves from here into the X9 register. Excellent. We can also see that we've hit the instruction here, and we're executing both states. That's exactly what we expect. Great. So if we come down here, we can see that the first thing the first state does right here is take the current M status register and route it into X2. Excellent. That's where the WD source comes in. Then the second state takes the mask that we have that's in the RSA and applies that to the CSR data, which we get the letter D. And that's exactly what we expect. And then of course the last thing it does is write that result into the M status register. So effectively we've done exactly what we wanted. We moved the current or the previous value of status into the X2 register and wrote the new bit configuration into the status register here. So this instruction is working exactly as expected. We're ready to look at the machine return instruction, but in order to do it we have to write an actual real big program, or at least biggest one we've ever written before. Here is the mReturn instruction that we're going to test. And the way we test that is by forcing an interrupt to occur. That interrupt is this little signal right here. This is where I've set up the loop code in C++ to interrupt this instruction while it's executing. Now, the way the specification says is that the instruction must complete first. So even though the interrupt occurs during the execution, it's in between the lines here during the prefetch stage that it will recognize the interrupt and jump. So let's talk about how this works. We know that we've set up our reset vector to point to address 100, which is where the boot starts, right here, address 100. We begin doing things like loading in different status CSR registers with different things. For one thing we want to do is disable global interrupts so that we're not interrupted during the boot program. And that's how we do it here. We load X1 with what's at 2008, which is right down here, and so this mask will disable global interrupts. You can use it also to enable global interrupts as well. Then we do a load mtvec. This would be the base address of where the handler is, which is at 180. So we know that this value right here should point to this location right here. Excellent, that's what we expect. And then we're going to load 2004, which is another mask for enabling and disabling M mode interrupts. So we've disabled the global ones, and now we're enabling the M mode ones. Again, no interrupt will be recognized until we enable global interrupts. And then finally we jump to main, and we don't care about returning here, so we use this structure right here. So main's address is at 0, and we're going to load 2008 again because we used it to disable interrupts. Now we're going to turn around and re-enable the interrupts with that exact same mask, and that's what this does. As soon as this does, this finishes execution, then any interrupts that were pending will fire off. Now none have been, no interrupt has occurred yet, but on the very next instruction an interrupt will occur. This is, again, that's the one we put in our C++ test bench. And as soon as that happens, as soon as it gets there, it will hit the trap routine down here. The prefetch will detect the interrupt and set up and call the trap vector. And now remember, we loaded the mtvec with 180, so when that interrupt occurs and it calls the trap vector, it knows where to go. And sure enough, here is our load BU. We just threw in a simple little call here just to give us something to execute in our trap handler. And then finally we hit the mReturn instruction. Now I put this e-break down here just in case we didn't hit it. It should never be reached. So the mReturn is going to pull off of the MEPC register. When we've executed when the prefetch executed right here, the one thing it did was store this address in the MEPC register. And so when this executes, it'll automatically reload the PC with this address and begin executing this instruction, and then finally we'll hit the e-break. So we'll be jumping all over the place, up and down until we eventually hit this e-break. So now we're ready to take a look at the simulation. Because the simulation is so big in this particular one, we're going to scroll through this and try to talk about the various things that we see along the way. For example, we know that the reset vector is moved into the boot sequence sector and is starting to run the instructions there. There's the first instruction in the boot sequence. If I scroll over, we're seeing here's the second instruction in the sequence. We'll move over here, and there is the third one. You can see that we're hitting different ones. Every time the right CSR goes high, we're hitting one of the CSR instructions. So here is the next instruction right there. There's the write to a CSR. Now we're hitting the load and then a final CSR, and then we hit our jump to main right here. This will jump to main, which means the program counter here will go to 0 and we'll begin executing instructions at the top of memory. And that's exactly what we're seeing. So far so good. Come here, we're doing the next, here's the next CSR instruction. Right there's the write. Excellent. And we know that on the next instruction I purposely have put in an interrupt, and right there it is. There's the interrupt, and you can see that it's executing the instruction. As soon as it finishes the instruction on the prefetch stage, it begins the interrupt phase of it, and it jumps to the interrupt handler, and there is the instruction at the top of the trap of the handler, the C0 instruction. Excellent. Keep moving along. We hit the return. Now we're hitting the MRET. This is the machine return instruction. Excellent. And it should return back to where the interrupt occurred, which is right there. There's the next instruction just after where the interrupt occurred. Excellent. Perfect. And as soon as it finishes executing that, it hits the e-break instruction at address 4 or 10 in this case in byte address. Excellent. So that was a real quick journey through the instructions of this particular one. Now we can go back eventually and look at a ton of signals, but we've looked at each one of these instructions in particular, and they're all working as expected, and this is great. This would be the only new instruction right here, the machine return instruction, and you can see that it has done exactly what it needed to do, which was reset the instruction to the next address that needed to be executed, and that's exactly what we were looking for. Now the better way to see this is in one of our later episodes. We'll use the ncurses simulation of it so that we can step through and see the values a little bit better. This is a lot of information in here, and it would take me quite a long time to go through every single one of them, but we have seen all of this information before. Awesome. We just implemented the CSR instructions and the MRET instructions and created a bunch of machine code to run them through their paces. However, as we saw in GTK Wave, it can be quite difficult to see the action through the forest of signals. So in the next episode, we'll update our ncurses simulation to include what we need in order to see our programs from an entirely different perspective. So until next time, peace.